So last time we talked about hypothesis tests where you have claims that involve two populations. So today we're going to continue that, talk about two populations instead of just one. But this time we're interested in the measurement of the two populations, not being proportions like last time, but being means. So comparing two population means. So let's put this in the context of an example. Let's say that we're looking at a particular standardized exam, let's say the ACT. And let's say that we're interested in knowing whether there's a difference in performance among female students versus male students. So let's say our claim is that there's no difference in performance between female students and male students on the ACT. So let's say in order to make a conclusion about the claim, we're going to have an observation with one or more samples, just like last time. And so let's say that we have two groups of students' scores. One is female scores and one is the male scores. And so let's say that we have a sample of let's say 100 female scores and also 100 male scores. And let's say we look at the sample mean for each. Female scores, let's say, is 26. Male scores, let's say, is 25. Oops, this would be X. So X1 bar is the sample mean for group 1, which are the females, and X2 bar is the sample mean for males. And let's say the standard deviation is 2. So the issue is that just by looking at the samples of females versus males, you see the average for females is higher by a little bit. But the question is that high enough to say that there's a real difference, or is this difference caused possibly by random chance? So we have to look at the underlying distributions in order to know and to make an accurate conclusion. So we're going to use hypothesis testing to do that. So again, the structure of hypothesis testing will be exactly the same as all the other cases we've talked about. The only difference is when we go to look at the distribution and to decide whether the observation is inside the body or the tail. That's where there's the difference, and we'll talk about that when it comes. Okay, so first step in hypothesis testing.
Mathematically make your claim and counterclaim.
Okay, good. So we start with this claim. What would the counterclaim be? What's the opposite statement?
Would not be equal to, so it would be the equal with the dash.
Yeah, so if the claim is that there's no difference, the counterclaim would be that there is some kind of difference, right? There is difference. And so remember, these claims and counterclaims have to do with population statements. So let's use a population variable. Let's say we're dealing with population mean in group 1 and population mean in group 2. So group 1, let's say we're calling female scores, and group 2 is male scores. But for the observation, there's a sample. But in our claim, the statements have to do with populations. So the mean for the whole population of female ACT scores, if we're saying that there's no difference, then what should the relationship be between female scores and male scores for their respective populations? Yeah, they should be equal if there's no difference. And if the counterclaim is true and there is a difference, then what should the relationship be?
Not equal.
Yeah, not equal. Another way of saying that is either greater than or less than Okay, so now that we have the mathematical statements, which one is the null hypothesis?
The first one.
Yeah, the first one, that'll be HO, and the other one will be H1. So now we're gonna go to step 2, which is we're gonna assume that HO is true. And in this case, assuming HO is true means that we're assuming mu1 equals mu2. Okay, so then, just like before, we're going to visualize this assumption. And the underlying distribution will depend on the variable that was used in the claim. So because we're using population means here, before when we were using one population mean equaling a number, what distribution did we end up using? Before in section 8.2, when we said,
distribution?
when we're dealing with a claim involving the population mean equaling a single number.
The
T-distribution?
T-distribution, right. Okay, so when we're dealing with population means, whether it's one mean or two means, in this case, then we use T-distribution. So that's the first difference, is to realize what kind of distribution we're dealing with. So population means in the claim means that we're using a T-distribution, and now all we have to do is label correctly the size of the tails and how many tails there are. So in this case, how many tails are there?
Two.
Yeah, very good. Look at H1 always, look at the number of inequalities. So this is a two-tailed test. So you can go ahead and label both the left tail and right tail. And I need to give you the confidence level. So let's say that the confidence level is 95%. So that means the body of the distribution is 95%. And what's left over, or alpha of 5%, is distributed across all the tails. So if we have two tails, that means each tail is how much?
2.5%.
Yeah, 2.5%.
And so where each tail starts, it's gonna have a critical statistic, in this case, a key critical.
Okay, so basically this is step 2 of hypothesis testing. We're just assuming HO is true and what the distribution would look like, and along with the size of the tails. So step 3 is now deciding whether the observation is inside the tails or not. So now we're gonna have an observation that has its own test statistic. Right now, I don't happen to know whether that test statistic is in the body or the tail. I'll just draw it in the body, and if it changes, we'll redraw it later. So recall that any critical statistic will come from a table, and any test statistic will come from a formula. So let's go ahead and find the critical statistics. So since this is a t-distribution, we're going to go to the t-distribution table. Recall the first column is degrees of freedom, which is, remember when we were dealing with one mean, then degrees of freedom is going to be n minus 1. But here we're dealing with two means. So basically the degrees of freedom will be the lesser of the two. So calculate n minus 1 for both, and then it'll be the lesser of the two. But in this case, it'll be degrees of freedom for the first sample is 99, second one's also 99. So they're both the same, so use 99. But in general, pick the lesser of the two degrees of freedom.
And for the table, we're still gonna use 100 because 99 is
The closest one, yeah. So you can either do area in 2 tails is 0.05, because we have a 2-tail test here, or you can do area in 1 tail individually is 2.5%. It would be the same column.
So 1.94.
Yeah, 1.984. Yeah, and this is area in 1 tail as 2.5%, 0.025. So T critical will be 1.984. So that's a critical statistic that you get from a table. Let's go ahead and find the test statistic. That'll be from a formula. So I'll write the formula up. So this is section 9.2. And so the formula will be t-test will be equal to x bar 1 minus x bar 2 minus mean 1 minus mean 2 divided by the square root of
Sample pool squared.
Yeah, so it'll be the sample standard deviation of sample 1 squared over n1 plus sample standard deviation of root 2 squared over n2.
Is this also assuming on the top where mean 1 minus mean 2 is gonna equal 0?
Yeah, good. So these are population variables, and the way that you know is look at what you're assuming to be true, because you're assuming something about the population to be true. So you're assuming that M1 equals M2, and because of that, if they're equal, then their difference has to be 0. Okay, so let's plug in numbers. What's x1 bar? That's from the sample.
X1 is gonna be 26 and X2 is gonna be 25.
Okay, good. So x1 bar will be 26. X2 bar will be 25. And again, mu1 and mu2 are population variables, and then we look at what we said about these population variables when we assume that HO is true. So if mean 1 equals mean 2 in the population, if they're equal, then their difference of equal numbers will be 0. So what's S1? Yeah, S1 is 2. And just so we can practice plugging these in, let's say that S1 is 2 and S2 is 3.
That changes things.
Yeah. Okay, so what t-test you guys, I think,
3.54.
3.54.
Using the original numbers.
Oh, that was the original numbers. 2 and 2?
Yeah.
Oh, okay.
Using the new standard deviation there on the right, for 3 instead of 2, it's 2.77.
2.77.
Yeah. Well, the first number there was correct for standard deviation.
Oh, okay.
Oh, so let's say it's 2.77. Okay, so looking back in the picture here, we have a two-tailed test with 2 t-criticals, and we saw that if the one tail was 2.5%, then t-critical on the right would be 1.984, but technically there's another t-critical here on the left. There's a left tail too. So what do you think that t-critical will be?
Negative 0.1.
Yeah, good. So it'll be the same value, but it'll be negative. So remember, this chart it only gives you a p-value based on the tail area, and it's assuming that you're feeding it a right tail, and it'll spit back a t-critical for that right tail. But if it's a left tail, it'll be the same value, just negative. But our t-test is 2.77, so is that to the right or left of t-critical on the right? It's to the right, so therefore it has to be inside the right tail, because it's to the right of where the right tail starts. So, t-test, now we can draw it actually squarely inside the right tail. So t-test will be 2.77. Okay, so now we can conclude that the observation is in the tail of the distribution, not the body. So now the conclusion that we make will be the same as before. If it's in the tail, then what conclusion do we make?
Reject.
Yeah, it's in the tail. That means the observation is not consistent with the idea of nature being true. So if you already have one observation not consistent with the idea, then you can go ahead and reject that the idea is true for all observations. So in the tail means that you can reject HO and accept H1. And you always want to bring it back to the original claim. So in this case, the original claim is which statement?
Original claim was the first one.
It's HO, yep, it's HO, so therefore, we look at what we said about HO, which is reject the HO, so therefore we can reject the claim. So in this case, we reject the claim that there's no difference in the scores, or we accept the counterclaim that there has to be a difference between the performance of the two curves. Any questions? So you see the only difference between this claim that has two populations involving population means is, first of all, the underlying distribution is a t-distribution because you're dealing with means. And the way that we find the critical statistic is from that t-table. The way that we find t-test is from this formula that will be good.
So, question on
Sure.
when it talks about,
Okay, so this is the alternative method. This is when,
I was trying to figure that part out, and I was coming up with different numbers, and I'm like, okay, I'm on the wrong side of it.
yeah, so this is the alternative method where the two population standard deviations are both known, but this almost never happens. So we're just gonna use the main one.
This,
Yeah, this will be this.
got that, and I'm tracking.
Okay, any other questions? So you see the general structure is the same as and consistent with what we've been talking about. This t-test will be a formula that will be given to you. You don't have to worry about memorizing this. This will just be in your book or on your formula sheets. Just calculate t-test, compare it to t-critical. We realize it's in the tail of the distribution, so therefore make this set of conclusions. Any questions? So that was section 9.2. So we'll move on and talk about section 9.3 today, and then we'll be done for today. So let's back up and look at the big picture of what we just did. We had a claim about whether there was a difference between female scores and male scores. And so we were interested in looking at both scores and their collective. So the overall mean of the females versus the overall mean in the males. We didn't care about the individual scores. But sometimes we care about the individual scores. And so for example, let's say there's a test prep company that claims that if you take their course, then your scores will improve. And so let's say that we look at two samples. One sample is before the course, the test prep course, and the other one is after the course. And let's say that you have a bunch of scores, like before the course, there's somebody who has, well, let's so you have a bunch of scores here. And then after the course, let's say you have a bunch of scores, but let me put them in random order. So you have a bunch of scores in some order before you take the course and a bunch of scores after you take the course. And let's say that they're same number of scores.
Is it a 2.5 or a 2.5?
Out of 2.5, yeah. So one way that you can determine whether the scores of the students are better after the course or not is you could take the mean of the collective and compare it to the mean of the other collective and see if the mean after you take the course is higher. Right, so that's one way that you could do it. You use hypothesis testing to see whether that's true for the entire populations of each group as opposed to just the samples. So that's one way that you can do it, but it's not the most effective way of doing it, because if you were somehow able to compare each student individually before they take the course versus after, if you knew this score was actually associated with this score over here, and you knew that this score was associated with this score, and so forth, if you didn't just look at the collectives of both groups, but you looked at the individual scores before and after, you looked at what we call the matched pairs. So now you match the pairs of each group. And let's say that you know that this score happens to go with this score, and this score goes with this score, and this before goes with this after. So that would actually be a much better way of gauging whether the course is actually effective, because now you're comparing each individual student before they take the test and after. So we call this comparing means of matched pairs, as opposed to comparing the means of the collective groups like we did before in the previous example. So in the previous example, all we did was compare the means collectively of the two groups, and you can think of that as comparing the means, comparing independent means. All right, let me phrase it this way. Comparing means of independent samples. So before, the previous example, if we compare test scores between females and males, there's really no benefit or no rationale for pairing each female with each male, because they're just random females and males anyway. But there is a rationale here for pairing a particular number from one group with a particular number of the other. It would represent before and after. So it would make sense to match pairs for the second example versus the first example. It wouldn't make sense to match the pairs, and we're dealing with independent samples in the first example. So another way of saying matched pairs is to say that they're dependent samples. So we're dealing with two different conceptual ideas. Before, we're treating the two samples collectively and comparing the means overall for each of those samples. And we're treating them as independent samples, where individual females of one group doesn't have any relationship to individual males of the second group. We're just treating them in the collective. Versus the second case, each data point has some relationship between of the first group with a data point in the second group. Because meaningfully, we're thinking of them as before and after the same person. So we say that those samples are matched pairs or dependent samples. So the only difference then is when we do hypothesis testing, ultimately, we're gonna have t-scores for both. The way that we find the critical statistics will be the same. You look in the t-score chart. The only difference is the test statistic. The t-score will be a different formula. But the hard part is identifying which formula to use. So if you're dealing with a case where you're comparing means of independent samples, then you use a different formula than what we just used. If you're finding a situation of comparing means of matched pairs or dependent samples, then you would be dealing with a different formula that we'll talk about. Any questions so far? Okay, so let's go ahead and set up this hypothesis test.
That's cute.
So let's look at these numbers that I had written up here. So we're dealing with before and after the course. And for each matched pair, let's say, so the 17 associated with the 19, 22 associated with
22.
22 again, 14 associated with 25, what's the big difference? 25 associated with 26, 24 associated with 25. So let's continue. So right now we only have 1, 2, 3, 4, 5 matched pairs. Let's say we continued so that we had a total of 40 matched pairs. But for each matched pair, let's say that we calculate the difference between the two numbers, before and after. So in this case, if we take 17 minus 19,
2.
we're going to get -2. So be careful with the sign as well. So we can take the first minus the second.
You did say the difference.
That's true, yeah.
My head.
Well, it turns out you can do either one, but the convention will be just the first minus the second.
Okay, so then you get 0.
0,
-11.
yep, good,
-1. -1.
and so forth, right? So let's say that you continue with all 40 matched pairs and you find the difference before minus the after. And so, then let's say that you take the average of all those differences. So the average of all those distances, we're gonna give a notation of d bar as opposed to x bar, which is the sample mean. D bar will be the mean of the differences. So let's say we have these 40 differences that we punch in our calculator, add them all up, divide by 40, and let's say the calculator tells you that it's -2.
And again, I think that really depends on how you're interpreting the data. Doing it this way, I mean, that actually indicates a positive result where normally we think that way with a negative sign.
Yeah. So this is just a convention that's used, and also group 1 could be the after group, group 2 could be the before group as well. So it just depends on what you assign as your variables. But once you've assigned the before group as group 1, then the convention is to find the differences is taking the first one minus the second. Okay, so let's say that your claim here is that the test prep course works. And by working, we mean improved scores. And just like before, we're going to test this claim with an observation. And the observation is in two samples of 40 students. So samples of 40, before and after. So you see that the average difference is -2. And let's say that we take the standard deviation of the differences. Let's say that turns out to be 3. So both these numbers, so this is what you observe, is the matched pairs. And let's say you type in these matched pairs in your calculator, and your calculator will give you that the average difference of the matched pairs is -2, and the standard deviation of these differences is 3. So again, so type in all of these differences, and let's say your standard deviation says it's 3. Any questions?
Do you actually want us to punch that into the list and try to make it say 3, or is that just the example?
No, this is the example, because there's gonna be 40 numbers in here. But let's say that after you punch it in, you're gonna get these summary statistics. This is the mean for the differences, this is the standard deviation for the differences. So this is given to you by your calculator after you punch in those 40 numbers for distance.
Where we substitute the D bar for the X bar, right?
Yep. Yeah, so punch in all these differences, and then your calculator will give you an X bar, that will be D bar in this case. Your calculator will give you an S, sample standard deviation, that will be S sub D in this case. Okay, so from this observation of 2 samples, you want to test this claim as to whether the prep course actually improves the scores. So let's step through with hypothesis testing. What would the counterclaim be? Yeah, prep course doesn't improve the scores. So let's go ahead and convert each of these English statements into mathematical statements. So the variable we're going to use pertaining to these population statements are mean 1. Well, this is
Dependent, wouldn't it be mean D1?
yeah, very good. So this should be mean 1 for D and mean 2 for D. So mean 1, remember, is the before group, that was group 1, and the after group is group 2.
So it'd be mean D1 is less than mean D2, because
Okay.
it's improving your score. That would be your claim.
Okay, good. So that means that for group 1, the average distance is equal to what?
If the claim is your course improved scores,
Right.
you would say that group 1 being before and group 2 being after, you would say that group 2 would be greater than group 1.
Right.
And the counterclaim would be less than or equal to.
Because the D's already take into effect, you're already consolidating the two groups, so let me make sure. Okay, so you only have one population mean for all the Ds. It's just like in the samples, you have, for this one sample, you have the sample for what all the Ds end up being. So we call that a sample mean for the Ds. If this group had represented the entire population of everybody before and after, all million people, for example, who take this test prep course, then you would have a million differences, and that would be a population mean for the Ds. So instead of a sample mean for the Ds, we're dealing with just one number that represents a population mean for all the differences between and before and after of everybody in the world who takes this test prep course.
Okay.
Okay, so if the test prep course improves scores, what should be this number? The average difference between before and after if the test prep course improves the scores.
Should be greater.
Well, we happen to be taking this notation where we're doing before minus after. So it actually improves scores.
Okay, so then you would say it would be equal to -2.
Well, if that actually improves scores, that means that on average, the before number will be lower than the after number. And so the before number minus the after number, if the before number is less than, then you should get a number that is, okay, so let's do the counterclaim first. The course does not improve scores. That means that there's no difference between the before and the after,
Okay.
right? So that means if it doesn't improve scores, that the average mean is gonna equal 0. The difference of the average difference is gonna equal 0. But if the test prep does improve scores, that means as a whole, the number before taking the course will be smaller, will be a lower test score than the number after taking the course, right?
Mm-hmm.
So then if you go to subtract a number that's smaller minus a number that's bigger, you're gonna get a negative number, right? So using the convention that we're doing, then if this claim is true, the prep course improves the scores, then the mean difference will be less than 0.
Okay. I'm gonna follow that.
So again, we're dealing with a population statement here. Everybody in the world who ends up taking this course, we're gonna track each person in that population, their before and their after. If this counterclaim is true and the course does not improve scores, then that average difference of before minus after for each group will end up just being 0, because the course doesn't improve scores. So the average difference for the population for each person will be 0. If the test prep course does improve scores, then the average difference of each person in the whole population taking the course, their after score will end up being higher than their before score on average. So the convention we're taking is we're taking the before minus the after, and so if the after score is higher, then this will end up being a negative number. So if the score does improve scores, if the course does improve scores, then this average difference before minus after will be less than 0. Okay, any questions? Okay, so now that we have step 1 of hypothesis testing, well, one thing left is which one is the null hypothesis?
The null is,
The counterclaim.
Yeah, the counterclaim is the null, so that'll be HO. The other one is H1. And while we're at it, H1 tells us that, how many tails are there?
There's only one.
Yeah, one tail, because there's only one inequality, left tail or right tail?
Last
Wow.
one.
Left tail, okay. Because it's pointing left, okay. So, let's go ahead and because we're dealing with a claim that has a population mean in it, again, we're gonna use a t-score distribution. When we go to assume that HO is true. Assuming the HO is true is that mean equals 0. Or, yeah, mean distance. So underlying distribution will be t-score. That t-score distribution will have tails, so let's label where the tails are. And the confidence level, let's say, is 95%. So that means alpha is
0.05.
the remaining 5%, 0.05.
But divided by 2 for 2 tails would be 0.025. We're only looking for 1, so we don't have to change anything.
Okay, good. So we have a one-tail test, left tail, so let's go ahead and label that left tail.
That's running out.
So this left tail has a critical statistic, in this case, T critical. And the total area of that tail will be what alpha is, which is 0.05.
So when you look it up with minus degrees of freedom, knowing that we have 40, we've got an actual number for 39. So the 1.685 is that?
Yeah, so first column is degrees of freedom, which will be n minus 1. We have 40 pairs here, so 40 minus 1 is 39. Go to 39, happens to be exactly in your chart. And go to 39 and go to area one tail, 5%. What's T critical show us?
1.685. Or area in one tail at 0.05.
Okay, good.
Degrees of freedom.
Okay, good. So 1.685, but notice this is a left tail. That chart is assuming that you're giving it a right tail, and that t-score will be positive. But because this tail is a left tail, this t-score will be negative.
T critical is negative 1.685. Okay.
Okay. So the only thing we have to do now is now we go on to the next step, which incorporates the observation. And now we just have to decide whether the observation is in the tail or the body. And so to do that, now we're gonna have a new test statistic. So that'll be so that'll be this formula, d bar minus the means, population means of the d's divided by the standard deviation, other differences divided by the square root. So let's go ahead and fill in the numbers. Again, this formula will be given to you.
But, so, assuming that the deviation with the, being true and that, mean difference is 0, you have, -2 divided by, 3 over the square root of 40. And you're gonna end up with, a really weird fraction of -4 with the square root of 10 over 3, converted to decimal as -4.2164, just to keep it short.
Okay, great. So d bar here is the sample differences. So that's given to us as -2. S is given to us as 3. The only thing that's not, and the standard, the sample size is given to us as 40. The only thing which is not a sample number is this population mean of the differences. That's a population number, not a sample number. So again, the way that we get that is from our assumption of HO. So the assumption is that the mean is actually 0. And so after you plug this all in, what do you get?
-4.2164. And I'm rounding up just to make that easier.
Okay, good. So we only have one tail here, and that left tail starts at negative 1.685, but we're at negative 4, so that's to the left of where that left tail starts. So our t-test is definitely in the tail of the distribution. So now what can we conclude about HO, if it's in the tail? Yeah, so we can reject HO being true. So if we can reject HO, what can we say about H1?
Except.
Yeah, so from this, we're gonna reject HO and accept H1. Bring it back to the original claim. The claim has to do with HO or H1?
The claim, has to do with H1.
H1, good. So then go back to what we said about H1, which is accept H1, so we're gonna accept the claim here. So we accept the claim that the prep course actually improves scores based on the sample data. So this is really powerful because just based on the sample of 40, we're able to make that conclusion about the entire population of students who take this course. Any questions?
Yeah, it's gonna be identifying the terms, it's the tricky part here.
Yeah.
Are these types of problems normally given with a table so we can put them in and figure it out, or is it assumed that that information will be given?
So be comfortable with both. So either you'll be given the raw data, like in this case, and you'll have to punch it in and calculate the summary statistics here, or maybe just the summary statistics will be given to you. Either one.
Does doing the formulas with the summary statistics is very easy. Is there a different method when using your calculator to compare two tests, when you're doing that two variable comparison?
Yeah, so the hardest case will just be if these summary statistics are not given to you, but the raw data is given. So then you'll have to punch in, you'll have to realize that this is a matched pair situation where there's a correspondence between each student being a before and after, and you want to keep those corresponded with each other, and then you figure out the differences between each pair.
So you match it on the individual list, putting in one side and then putting the other with the corresponding pair, and then you get your data off the two variable stats, right?
No, so what you would do is just look at each data point of before and after, and you just find the difference. And then once you have these 40 differences, punch those differences individually in your calculator.
Okay, right.
Yeah. So you don't need to punch in the raw data. From the raw data, you calculate the difference of each pair, and then
Then
punch
you're only
in.
computing one list. Okay.
Yeah, one list. So type in the 40 numbers for one list representing these differences, and then your calculator will give you a mean and a standard deviation for those 40 differences. So now you're back to this case. So this is the matched pairs case, where it makes sense to match the pairs. The previous example we did, where we had female and male SAT scores, or ACT scores. In this case, you have, let's say, 40 random females, 40 random males. It wouldn't make sense to match a female with a particular male. So in that case, this is not a matched pairs case, and you would enter in the 40 females, get their mean for that group collectively, and then enter in the 40 males and then get their mean. So now you have a sample mean 1, sample mean 2, and then you're back to the previous case for the non-matched pairs.
Because it's independent instead of random.
Right, because
It's
for each
independent.
data point, it would not be advantageous or extra advantageous to match each data point with another particular data point in the second data point.
The dependent independent is the part that comes into play there. That's what I was trying to say the first time. And I started out wrong, right?
Oh, okay.
Because here, they are independent data points, where when you're doing the matched pairs, they are dependent data points, where
Yes.
you can make one list and compute it.
Yes.
Here, you have to make two differences and figure out the difference between them and how it's actually gonna show up.
Good. Okay, great. Any questions, guys? All right, so for today, have a good day. Yeah, the only changes is if you attempted any homework late, where there's, or you didn't attempt anything, then later there's gonna be zeros. But other than that, there's
Yeah, I
a-
attempted everything and I got a
okay, good. So there's no changes.
No, I 100% figured it out, it just took me a while to figure it out. You're good.
Do you mean for the confidence intervals?
Yeah.
Yeah.
And then, figuring out what side of the table, or what side of the table you're actually looking for, when whether you need to subtract from zero or not, right? So, the, negative p-score, or a negative test result normally puts you on the right side, where you don't have to compute from the other side. If you're positive, we're doing